I'm hoping that by this time you've had a chance to do the reading, both the book reading and the online reading. I'm going to be talking about binary trees and then specifically about binary search trees. Remember that we're going to do build our own binary search tree, and that'll be due at the end of the week after break. So not during spring break, but at the end of the week after spring break, our first assignment will be due, and you want to look at the assignment after you watch this video. So let's go through and talk first about binary trees. Our objectives are to learn about binary trees. We're going to learn how to represent and handle a binary tree using the tree node class. So we'll find that the binary tree and the binary search tree is similar to a singly linked list. That the singly linked list used a list node, and here we're going to use a tree node. And we'll see a tree node is a lot like a list node. It's just a little bit more complicated. And then once we learn about binary trees, we're going to learn about binary search trees. So a little more specific. We will not talk about sets and maps yet. All right, so let's first just talk about trees in general. And the diagrams that you see here are not binary trees. These aren't binary trees. A binary tree is a tree that is going to branch, and it's always going to have at most 2 branches. And you'll see that on the tree that's on the left, there are 3 branches in one case, and there's a 4 branch. So these are not binary trees, but they are trees. And the terms that we're going to be talking about in these diagrams have to do not only with just trees in general, but also binary trees. So up at the top of your tree, there's that first node, and we'll find that these are tree nodes, is called the root, and that's where you're going to start. When we talked about singly linked list, I talked about how you had to have a place to start. You had to have first. I used the paperclip analogy, where you had have that first paperclip up at the top, and then you can get to everything else. And it's very similar when we're talking about a tree, and a binary tree in particular. You're going to need to have a place to start, and so instead of having a first where you're going to start with a root. And then once you have root, you can either go left or right. And so if you go left, that's the left child. If you go right, you have the right child. And you can keep building off of that, and you can kind of get a bushier and bushier tree as you go. Again, these diagrams are not binary trees. These are just trees in general. A binary tree will just have 2 things branching off, just a left and a right. If you do wind up with a node, so the individual elements are called nodes, they'll be tree nodes. If an individual node has no children, it is called a leaf, or plural leaves. So you should know those terms. You should also know the number of levels. So you just count from the top, from the root, and then go down the number of levels. So each of these diagrams that you see, both on the left and the right, have 5 levels, starting with the root and then going down to the lowest level of leaves. We can also talk about subtrees. So if you take a look at the diagram on the right, you can take a particular node and everything that is attached beneath it. That's called a subtree. And there are lots of subtrees you can break these trees into. So again, diagrams of trees in general, and we'll be working with binary trees. All right, so some good things about this data structure are that a shallow tree can hold many nodes. So if the tree is well balanced, then if a tree has 20 levels, it could have as many as 2 to the 20th minus 1, because you're doubling the number of elements in each level. And so that's a lot of nodes that you can have when you have a relatively few number of levels. And when you reach a node, you can make a decision to go to the left or to the right, and how to process the tree. And the path to the bottom, again, is relatively short as compared to the total number of nodes. All right, so we talked about nodes, and when we're working with a single linked list, we use a list node. So you might want to go back and review the list node class. When we're working with a binary tree, we're going to use a tree node class. So remember that a list node will hold an object, and then it would hold a first element. And we could add a last, but let's think of the simplest case of the list node class, where it held an object and then it held another list node, which was first. Well, here we're going to move from 1 dimensions into 2. So a tree node is going to hold an object. It might be an integer, it could be a point, like it was in our last programming assignment. And then instead of holding one other list node, it holds 2 tree nodes. You can go to the left or you can go to the right. So again, think of that list node idea, going from 1 dimension into 2. And the tree node class, again, looks a lot like the list node class. There are a couple of constructors. So you can construct a tree node so that it is a leaf. It doesn't go left or right. It points to null. Or you can construct a tree node. This is the second constructor, where maybe it's got some other valid subtrees to the left and to the right. And then there's a get value, much like there's a get value method in the list node class. And then instead of get next, as we had in the list node class, there's get left and get right. You can set a value, much like the list node class. And then instead of set next that we had in the list node class, here we have set left and set right. So just a little more complicated than the list node class. We'll find that solving problems with trees, binary trees and then binary search trees in particular, lend themselves to recursion. So here's a relatively simple method that will go to all of the nodes of our binary tree by using recursion. And the base case here is when root equals null. It's not stated explicitly other than in the comments. So you only do something if the particular node you're at, which is called root as you pass it in, the particular node where you are, if it's not null, then you do something. But if you reach a leaf, then you're going to get to a place, if you go left or right, you're going to get a node that is null, and so that's where you're going to stop. And when you see the process method here, it might just be something as simple as printing what you have. So think of maybe instead of process, maybe it's just a print. You print a numerical value if they're integers. So you can process, and then you can go left and you can go right, and you're using recursion. So this would print all of the elements of this tree, and think of it as a binary tree, by printing and then going left and going right. Here's another simple, short, recursive method that would count the number of nodes that were not null. So we're just counting them. Again, root is just a stand-in for the name of the node. So you would start up at the top, which is the root of the tree. And then if you reach one of the leaves and you go left or right, then you're going to get a null tree node. So you wouldn't count that. Otherwise, you're going to say 1 plus, and then you're going to go to the left and you're going to go to the right. And if those are valid subtrees that are not null, it'll keep doing the recursion and counting every element, every object value in the tree node that is where you don't have a null tree node. So a recursive example. All right. So I'm going to post some videos about pre-order and in-order and post-order traversal, and it's something that you should know relatively well. So you can traverse in pre-order, and with pre-order you do the printing. Again, instead of process, just think of maybe just printing. Here there are capital letters. So you would print, and then you would go left, and then you would go right. So you want to check out those videos. Here's a very simple example of pre-order traversal. Here's in-order traversal. Notice here you go left and then you process or maybe print. and then you would go to the right. So notice the difference between pre-order and in order. Again, watch the videos that I have, the short videos about these traversals. And then the last one is post-order, where you go left, you go right, and then the last thing you do is you process, or again, think of printing the object value that is at the particular tree node. So here's a brief summary of the idea. So pre-order, you deal with the root first, then you go left and right. In order, you go left, and then you deal with the root kind of in the middle. And post-order, you go left, right, and deal with root value. And where you see root, you might think of printing the value. Where you see that term root, think of printing, whether it's a letter, as in the previous examples, or maybe they're numbers, could be integers, as you see here. All right, so we are going to be working not just with binary trees, but we're going to be working with binary search trees. And binary search trees are binary trees where your data, your objects, are in order. They're in order. So you're typically going to work with comparable objects. And for each node, all the values to the left subtree are less than, smaller than the value in the node. And all the values in its right subtree are larger than or greater than the value in the node. So the examples we see here on the left, it's not a binary search tree. Oh, I'm sorry. Well, on the left it is a binary search tree, but on the right it's not, because that 8 in the right subtree is not greater than 12. So it's not considered a binary search tree. But the one on the left satisfies the rules, right? If you go 15 and you look at that left subtree, 1, 8, and 12, everything is less than 15. The 20 is greater. If you look at the 8, when you go left, everything is less. When you go to the right, the 12 is greater, so it's a binary search tree. All right, so some advantages that a binary search tree might have, this data structure might have over some other data structures, is it's quick for searching. If you have a bushy or kind of a well-balanced tree, we talked about how if there are just 20 levels, you could have close to 1 million or around 1 million elements. So you could search it very quickly, and then you can also insert and delete values relatively easily, just as you can in a linked list, whereas in an array and an array list, that's a little bit more costly. So it does have some advantages. It's not going to be, you're not going to be able to access the elements quite as quickly as you can in an array or an array list, where you can just use index values. And it is a little harder to insert and delete than it would be for a singly linked list, but still it combines some of the advantages of other data structures, kind of in between. All right, here is a recursive method that uses contains. Here I'm going to show you contains method that uses recursion, and then another one, the next slide, will be an iterative solution to this. So here we're looking for a target value, and here we're assuming that the object values that are held in the tree nodes are strings. So if you get down to the root being null, if you get down to a leaf and there's nothing left and you go left or right, then you're going to return false. But remember, this is a binary search tree, so it's in order. So you should be able to go left or right depending on what you're looking for. So you either go left or right, and then you find that if the difference is 0, that would mean that you found the string that you're looking for, then you would return true. Otherwise, you look to go left if you're looking for something that is less than, or you go right if you're looking for something that is greater than. And again, you'll eventually reach a leaf, and you go left or right, and it'll be null, and you'll find that it doesn't exist in your binary search tree. Or you're going to find the target when the difference is 0, and you're going to return true. So this is a recursive solution for contains. Here is an iterative solution for contains. So you're looking for a particular string in your binary search tree, so it's an ordered binary tree, and you are going to take the node that where you currently are in the binary search tree, and while it's not null, you're going to calculate the difference, and then if you find it, right, if you find the string you're looking for, you'll return true. Otherwise, you're going to go left or you're going to go right. And again, you're going to keep going down the binary search tree in the correct order because you know that everything is ordered. And if you never find it, if you eventually get to a node that is null, that means you've reached the end of the tree where your particular word, your particular string should be. And so you would kick out of the loop and then you would return false. So you've got, again, the previous slide. This is a recursive solution to looking for a string in a binary search tree. And the next one is an iterative solution to finding a string in a binary search tree. You want to make sure that you understand in a binary search tree, and here we have integers. If you're looking for the smallest value in your binary search tree or the largest value, it's not necessarily on the lowest level. It's not necessarily on the lowest level. So here, the smallest node, and here we have 4 levels, is it's 2 levels down from the root, and it's not at that 3rd level from the root. So you have a 7, which is the least value, and a 51, which is the largest value. So don't assume that your largest or smallest value is going to be a leaf. And here the tree node that contains 7, the tree node that contains 51, those are not leaves because they do have something that is below them. So make sure you understand that about binary search trees. Again, notice everything is in order here in this binary search tree. All right, so when a tree is balanced, add, remove, and contains will take on the order of log n, and it'll actually be log 2. So that's pretty fast when you're looking for something. You do have to be aware that if you add nodes randomly from a set that where you're trying to create a binary search tree, you can get a binary search tree that might degenerate into looking more and more like a single linked list. So there are ways that you can kind of rearrange things in a binary search tree to make it balanced, because that's important. It's important that your data structure be easy to search, be easy to add and remove. And so there are algorithms that you can use to get that done. All right, so that's it. And you want to make sure that you are looking at the next assignment. Remember the first assignment on binary search trees, it'll be due at the end of the week when we come back after break.